Hello everybody, my name is John Mark Johnson Jr. I am the host of Reformed GGA, and today I wanted to talk a little bit about firearms safety as it pertains to starting wildfires. What prompted this video was actually a video that I recently saw over on the MAC channel, the Military Arms channel, in which Tim, who is the primary host of the Military Arms channel, revealed that he had accidentally managed to set his personal range on fire. And he went over the basic conditions of what happened, and he also went over a lot of good information in terms of general safety and precautions and contingencies and those kinds of things. All of that is well and good, but I wanted to just add to that some information that actually comes from one of the very few studies that was actually done to try to understand what makes ignition by specifically rifle bullets in this study, what basically makes ignition from firing firearms outside a more likely versus less likely scenario. Now, it should be noted that this study, which has a very boring name, as most of these kinds of studies do, this one is called A Study of Ignition by Rifle Bullets by Mark A. Finney et al. This study, even though, like I said, it has a very boring title on it, and it should be noted that this study is put out by the government, specifically by the United States Department of Agriculture and the Forest Service. And because of that, this study should be viewed with a fair degree of skepticism, because these kinds of studies are usually put out with a very, very, very strong left lean. They're basically a bunch of bleeding heart leftists over there at the Forest Service, and so their opinions are not exactly going to be unbiased. But, like I said, there is still information in this study, some very basic facts that they would agree with me on, and so I'm using their study because it supports the basic points that I'm going to be revealing. But like I said, it is a very left-leaning study. If I remember, I'll go ahead and put a link down in the description box so that you can go and peruse the study yourself. And like I said, it's definitely left-leaning. But nonetheless, there's good information here that people who are interested in shooting outdoors will want to be aware of, so that they don't cause, unnecessary damage in the form of wildfires. First, just kind of to show the somewhat biased and not entirely reliable nature of government studies, I'll point out one table here that they have that goes over some of the guns that they test fired, the ammunition with which they test fired it, and also includes the muzzle energy of these, the supposed muzzle energy of these firearms. And if you look through this table, you will very quickly figure out that whoever did their muzzle energy tabulations was a bona fide idiot. For example, they say that a Colt M4 firing Remington UMC with a 55 grain bullet traveling at 2,900 feet per second produces a muzzle energy of 2,054 foot-pounds of muzzle energy. That is ridiculous. Okay, an AR-15 with a 55 grain projectile traveling at 2,900 feet per second will not get you that much muzzle energy. Most of the time with AR-15 type guns, you're going to see usually somewhere between 1,250 and 1,450 foot-pounds of muzzle energy. They are nowhere near 2,000 foot-pounds of energy, let alone more than 2,000 foot-pounds of muzzle energy. So whoever was doing these calculations was on crack, and they should not be taken overly seriously if they can't do a basic computation like that and don't understand why that would not be reasonable. But, like I said, there is some basic results that they got out of this that is worth talking about. To get to those results first, we have to talk about the test. And the test rig that they set up was actually fairly straightforward. What they did is they took a steel plate. They later changed this out for a granite plate later on in the test, but most of the data comes from the steel plate. So they took a steel plate and set it at an angle over a box that was filled with very, very dry peat. and then they would shoot into the steel plates. The fragments would then be deflected downwards into the peats, and then they would go and check and see if that would result in ignition, and they would usually fire 5 rounds at a time. So lots of hot lead and copper bouncing off of a steel plate, usually fragmenting into tiny little shards after hitting the steel plates, then going into very dry peats pretty much immediately. Basically, they set up a test rig that was as prone as they possibly could to giving them ignitions. So the fact that in this study they got an ignition a lot of the time isn't overly surprising given the rig that they set up. They basically, made it most likely to result in an ignition, most likely to result in something that could start a fire. So yeah, the study was kind of rigged from the first hand to produce fires, but like I said, the point of this study isn't so much to prove that bullets can cause wildfires. They can, that's not really in dispute in and of itself. It's under which conditions they're most likely to cause fires that I want us to get out of this. Alright, so in terms of things that could be changed on this setup that would affect how likely you are to get ignition here. One of the things, of course, is going to be whatever your target area happens to have as its base medium around it. In their case, they used very dry peat because that is very likely to burn. They wanted to get ignitions. For us as shooters, when we go out, one of the best things that we can do is make sure that the area around our targets that are most likely to get hit by bullets are not of things that are particularly flammable. So around our targets, and especially behind our targets, we need to make sure that they're clear of dry grass and other various dry debris that burns easily. Simple enough. Additionally, they kept their hard target very close to their medium. Like I said, the plate was basically attached directly to the box that contained the peat, which means that there wasn't a whole lot of time between the fragments being formed on the plates and those fragments hitting the peat in the pan. This study revealed that the time that it took these shards to basically dissipate in terms of heat actually wasn't all that much. Here is one of the sets of graphs that they have that record the temperature of these fragments, and you'll notice that it starts very high for a lot of these ones, but within literally just a few seconds you get down to basically a baseline amount. And of course, the point at which you're going to get ignition is usually at the highest point, which settles down very, very, very quickly. So in terms of watching your range, most of the risk is going to come, within about 30 seconds or so of firing a shot. And for most of the ammunition, as long as you don't get ignition within 30 seconds, you're usually good, basically. So, yeah, whatever you can do to increase time between when the fragments are formed and when they contact the substrate around them is going to be an improvement. For those of you guys who use steel targets, what this means is that you actually want to hang those steel targets basically as high off the ground as you can. Now that does produce more of a ricochet risk to you, the shooter, which would need to be offset by putting those steel targets further out. But the higher your hard targets are off the ground, the less likely the shards that come off of that hard target, the less likely those shards are to cause a fire. So you can increase the height. You can, of course, clean the area around your targets and behind your targets of anything that is flammable. And another thing that they found that was very interesting was, of course, the angle at which that steel plate was held. They tested between 20 degrees and 80 degrees, 80 degrees being nearly vertical. So their angle that they're measuring is basically the angle of inclination, or inclination, depending on how you look at it. Where is the diagram that shows that? There we go. There's the diagram. So this angle right here, they found that as this angle got wider, as this plate was pulled up higher, that the probability of ignition went down, and it went down pretty significantly. So towards 80 degrees, a lot of the probabilities of ignition were cut in half or more in a lot of the rounds. And you got to the point where some of the rounds, types of rounds that were fired, were just basically as safe as other ones would be if you hadn't adjusted the target surface. So the kinds of projectiles that they tested were as follows. We'll start from the bottom here. Least probability of ignition was lead core copper jacket bullets, which are fairly standard plinking rounds. Most of the plinking rounds that are out there have a lead core and a very, very, very thin copper jacket, and it turns out that those have a very low probability of ignition. It's not impossible. They got it to happen, but even with a fairly severe angle where you're basically skimming that bullet off of that plate for a prolonged period of time, increasing the contact time, increasing the amount of sparks that are going to be generated, and increasing the heat that those fragments are going to leave with, that even under those conditions, going right into dry peat, they found that lead core copper jacketed bullets didn't have a particularly high probability of ignition, starting a little bit above 10%. They have the probability over here on the side. They're just listing it as a decimal. For those of you who don't know how percentage probability works and decimal probability works, it's pretty easy. You basically just move the decimal point over 2. So 0.1 probability is the same thing as a 10% probability, 0.2 probability is the same thing as a 20% probability, and so on. So lead core copper jacket, even with a very, very, very shallow angle with the most contact time with the steel possible, basically, that they could generate in their rig, was still somewhere between 0.1 probability and 0.2 probability, so between 10 and 20%, closer to the 10% under the worst possible conditions. You raise that steel up so that your contact time with that steel is minimized. They were able to get as high as 80 degrees, and the probability of ignition went down to pretty much a negligible level. What is interesting is that steel core projectiles with the copper jacket and lead core projectiles with a steel jacket start out pretty high in terms of their risk of causing ignition. If you're firing them against something hard that they're meeting at a very shallow angle with, very high probability of ignition, but as you increase that angle, make the hard surface more and more upright, more and more vertical, the chances of that leading to ignition drops dramatically, so dramatically, in fact, that the low end of the steel jacket or steel core projectiles causing ignition actually overlaps with the lead core copper jacket causing ignition. What this means practically for us as shooters is that if we use steel targets that are hung basically vertically to us, and we stand them, put them on stands that are fairly tall, that we are going to greatly reduce the chance of causing ignition with either the lead core copper jacket bullets or with the steel core copper jacket bullets. If you're firing them under those conditions, they're both fairly negligible in terms of risk of causing a fire. Now, that being said, there were two types of ammunition that were absolutely atrocious when it came to ignition probability, and even if you tried to give them the best conditions to not cause ignition, they were still pretty likely to do it. And that was projectiles that had both a steel core and a steel jacket, and solid copper projectiles. The solid copper one was actually somewhat surprising, because the Forest Service and various environmental groups and government groups usually suggest that recreational shooters and hunters use solid copper bullets because it's supposedly better for the environment. Lead, of course, is poisonous, and so they say instead of throwing out a bunch of lead bullets, we would prefer that you put out a bunch of solid copper bullets because it's not nearly as toxic as lead is. That's the reasoning. What is interesting is that this study, though, proved that solid copper, while it might not be as poisonous as lead, it can also it is also much more likely to cause ignition than a projectile that has lead as a component. And that is because these copper projectiles, when they hit a hard surface, they do break into fragments like the other ones do, but those fragments tend to be very large and they tend to retain heat relatively well, which means the incidence of ignition tends to stay really high regardless of what the impact angle is. Yes, it does decrease as the impact angle increases, meaning the more vertical you hang the object, the less likely it is to cause ignition, but it is still incredibly high. It's still around 0.5, around 50% ignition in this test, even with a fairly vertical surface. And steel core, steel jacket ammunition is not far behind. So yeah, neither of those are particularly good for firing outdoors, especially if you have any kind of dry brush around or anything like that. They're not really good in terms of starting fires. Like I said, I know that a lot of the government entities will say, okay, we don't want you to use steel component ammunition out here at this particular open spot of ground, but solid copper is just fine. Well, if they were being consistent with what the data actually shows, they would actually restrict the solid copper projectiles and the steel core, steel jacket projectiles and not be as concerned with the other ones. But the government is hardly ever consistent, and so that's not going to happen. But if they were consistent, that would be the case. And then another thing that we can learn from here is some of the studies that they did in terms of temperature. These are some of the graphs that they have of temperature with different projectiles and different construction. And you'll notice that the temperature spikes are usually very short, usually just a matter of seconds before these things usually return to their normal state. The only exception would be those solid copper bullets. Those don't tend to lose heat very well. They tend to retain heat instead. But most of the other projectiles, they lose their heat from being fired at a hard surface relatively quickly. And so in these graphs, you'll see the impacts on this bottom left graph that we have right here. You basically have 5 shots, and you have the heat markers for those 5 shots. Notice initially those sparks that fly off of the hard surface, off the steel, their temperatures are very, very, very high to start with, but they cool down very quickly, so quickly that basically becomes part of the background temperature by the time you get to the next shot, which is usually just a few seconds away. What does this mean for us as shooters? It basically means that as long as we go and we check our target areas and spend a little bit of extra time there, for the most part, if you don't see fire fairly quickly, there probably isn't going to be fire. For most cases, firing relatively normal ammunition, waiting 30 minutes after you're done firing, checking the range, making sure that there's no smoke anywhere, no flames especially, is usually more than sufficient. Like I said, unless you're talking about solid copper projectiles, because those can maintain their heat for a lot longer. But for the most part, the primary heat dissipates really quick, and as long as you do the courteous thing of waiting at least a half hour before leaving after you finish shooting, which is usually time that you would spend going and collecting your targets, collecting your brass or whatever, as long as you're spending a little bit of time extra, you're usually okay. And of course, as Tim mentioned in his video, bring fire stopping equipment with you. A fire extinguisher is always good to have on hand. A bucket or a set of buckets if you're next to a water source is good. And then don't forget the value of a good old-fashioned blanket or canvas that you can use to also put fire out as well. And blankets and canvas actually have a lot of utility that way. You just cover the fire and beat it out, basically. That's actually not a bad way to go, and much lighter to carry than a bucket of water. Alright, so those are some basic things that we can learn from this study. Like I said, basically, if you're going to set up hard targets, set them up at a fairly high angle. You want them to be nearly vertical. That does result in a greater probability of you possibly being struck by a ricochet, but that can be mitigated by putting the hard targets further out. Clear your target areas of dry brush and debris, and also do your very best to clear your area of rocks, because the surfaces of rocks, of course, are not very predictable, and that causes problems. A proper backstop is not rock. A proper backstop is basically dirt. That is ideal, or sand, something along those lines. Alright, that is all that I got for you guys. Hopefully that made sense. Fairly vertical targets placed high off the ground with basically dirt as your surrounding material gives you a very good protection against causing fires. Alright, everybody, thank you for your time and attention. For those of you who are with Christ, go with God and be blessed. For those of you who are not, I pray that you would come to know Him, the only true Savior of humanity, and its true King of Kings and Lord of Lords. Amen.